before that I will present a strain compatibility method that may be helpful for your research and for even for other analysis methods, even including steel reinforced bars or titanium bars. I had a project with titanium reinforcement, very expensive. Titanium is very expensive. But the recycled titanium, what happens is the aerospace industry, they use a lot of titanium. But they will not accept titanium even if it has a very small defect. So they reject a lot of the titanium plates, the titanium material, because even if they find out a small defect, they throw it. So recycling titanium is a big potential market. So we take that, and I have a company who actually melts and makes sheets out of reject titanium or recycled titanium. So we are working on that. So you can use your strain compatibility method even for titanium. There is no code of practice for titanium reinforced members, right? Obviously, there is nothing. So you can use, if you are using some new material or some new design, absolutely, unusual design, you can use strain compatibility method. So that's what I'm going to present in next 10-15 minutes. So strain compatibility method. So in the strain compatibility method, we'll relate this to FRP, so it all stays together. So in under reinforced section, what did we do? ACI gave us an approximate equation, right? And then we used it blindly. We said, okay, ACI is saying so it's fine. But if you really want to use your own analysis, you can always develop a strain compatibility worksheet. So here, just recapping what we already know, we all know this really well. In this case, our strain in strain in the concrete at the top fiber is likely to be less than 0.003 or 0.0035, right? It's under reinforced section. But at the bottom, you can have epsilon FU, which is the strain at failure for FRP. So the corresponding stress can be triangular in shape, parabolic in shape, parabola plus rectangle in shape, or it can be perfect parabola. Anything you want to assume, it's possible, except that it should match with the maximum value of strain in concrete. So if the concrete strain is very small, then it's highly unlikely you will get a perfect parabolic stress strain diagram or perfect stress block. Okay. Now, how do I deal with that? I cannot, ACI says use this approximate stress block. Okay, that's fine. That's good for daily design. But if you are trying to test a beam with, and you want to get more accurate results, strain compatibility method is what will give you a better result. In this case, again, we have two unknowns. One is the strain in concrete, because it cannot be 0.003. It has to be less than 0.003. So we don't know what the strain is. And then depth to neutral axis C. And the concrete strain may not have reached 0.003. That we know. Therefore, rectangular stress block cannot be used. So in this case, you have two materials. One is concrete, the other one is FRP. In your design, if you want to try something else, you may want to add steel reinforcing bars, okay? Or you may want to add something else fancy, I don't know, whatever, right? So you may add something else. So it need not necessarily be just concrete and FRP. It can be something else. In that case, the first thing you will do is either you do it yourself or you ask the supplier to provide you with stress strain relationship of the material. If you have FRP, give me stress strain curve for FRP. If it is, let's say, high strength steel, then you can always ask for stress strain curve for that high strength steel. So strain compatibility method doesn't recognize the material. It can be any material. I have used it for aluminum beams, beam design in aerospace industry. I used for titanium reinforced concrete. I have used it for many applications. Okay, so the main thing is you should have accurate stress strain curve for the materials, how many ever you have in your section. And then we need to lay out the actual analysis. And as I said previously, or maybe I did not say it, but it's a trial and error method. That means you assume something, you get a final result. If the final result is not matching your target, then you go back and change your assumption or adjust your assumption to get the final match. That's what it is. That's a trial and error method. The main assumption in this analysis is the strain diagram is linear. That's the key thing, most important assumption. So once you say it's linear, that means the plane sections before bending remain plane after bending. If that's valid, in some cases it's not valid. Particularly for deep beams, for wall design, they may not be valid. The plane section assumption may not be valid. But for most beams it's valid. You can always draw the strain diagram. That's my starting point. I draw a strain diagram, and then this will be a linear diagram. That's what it needs to be. And then at each level, I can divide this into, like above the neutral axis, I can divide it into many different sections or layers. Here I am only showing 1, 2, 3, 4, 5, 6 layers. You can have 20. If you have a nice Excel spreadsheet, you can have 100. It doesn't matter. More the layers, more accurate your calculation or integration will be. If you are very good at math, you are able to integrate your shape with your stress strain diagram. That's even better. You can do it that way too. But if you have discrete elements, like if you have reinforcement here, let's say steel reinforcement here and here, FRP here, in that case you can mix and match your strain with the material that you are using. So now I have a strain diagram. I assume some amount of strain here. I assume some depth to the neutral axis C, and then I'll just run the numbers. I'll find out strain at different levels, the corresponding stress at that level, mid-height level, and then I will combine the total elemental stress multiplied by area. That will give me the force. So at different levels I will have different forces. I will sum all these forces. Below the neutral axis I will have force in the opposite direction. So all the sum of all these forces should be equal to 0. Right? That's for equilibrium. That's all. It's as simple as that. So for for this strain compatibility method to be accurate, you need very good stress strain curves, very reliable stress strain curves. You need it for concrete, you need it for FRP reinforcement, or if you have other type of reinforcement like steel bars, you need stress strain curve for those as well. In a way, in your beam columns, you are actually using strain compatibility method without actually calling it strain compatibility method. So for reinforced concrete, you have one of the well-known stress strain curve is Desai-Krishnan's curve. It's a very old curve, like 1960s or 1950s, something like that. Desai and Krishnan both are professors in Kharagpur, IIT Kharagpur. And this is a very handy equation for stress strain curve, and it's still being used by many people. Of course, they have made some adjustments, and people are using other forms of parabolic curves. And then Kent Park, again, Park is from New Zealand. He's now more than 90 years old. Of course, I don't know if he's still alive, but they have this. So this is another stress strain curve. There is also other curves for high strength concretes. there are lots of curves being published in recent journals. Okay, so you can use any of those. Collins, again, they have another stress strain curve. The only problem with this one is integration of this equation can be kind of difficult. It's kind of tricky, at least for me. If you are very good at math, you probably can integrate it, but average student cannot integrate this equation. So if you plot these three equations, I have shown only three, there may be many others. It will look something like this. On the x-axis you have strain 0.001, 0.002, 0.003 and so on. Without any variation, all these curves assume that the peak stress is reached at 0.002, a strain of 0.002. Okay? That's a common thing for every equation. Now, before reaching 0.003, 002, all these curves have almost same variation, very little difference. So if your strains are very small, if epsilon c is less than 0.002, it doesn't matter which equation you use, you will get exactly the same answer, because the variation here is very, very small, right? Beyond the peak, the post peak, of course you have three different steepnesses here, but from my work I found out that these falling branches of these stress strain curves are not making much difference in the final analysis. Okay? You may find a different conclusion, but that's from what we did. In most cases we did not find much difference, maybe 1 or 2%, maybe maximum 3%. For steel we have stress strain curves. Depending on the type of steel you are using, you may have this kind of nonlinear relationship, or you may have mostly bilinear relationship. So generally bilinear relationship is adequate for most analysis, and for FRP you will have perfectly linear relationship. It becomes very simple if you are using FRP, right? So in the next 4 slides I have step-by-step procedure laid out for all of us. Okay? If it is you can design or you can analyze an over-reinforced section or a balanced section or an under-reinforced section, any section, it doesn't matter. You can analyze any section using strain compatibility methods. Okay? So if it is an over-reinforced section, we know that failure is by concrete crushing, which means my strain, concrete strain at the top fiber reaches 0.003 first. Okay, if you are using IS 456, that will be 0.0035, but that's something we already know very well. Then first thing you'll do is try some value of C. So that, let me call that C trial. So you divide the compression block into many layers, many layers, and at each mid height of the layer, first of all you find out the distance. You can go back to here, find out the distance from here to the mid height of these layers. So that's the distance di, let's say it's di, and from your corresponding strain diagram you can find the strain at mid height of each of these layers, right? So each strain has a corresponding stress depending on the stress strain relationship of the material. If you have reinforcement here, steel reinforcement or FRP reinforcement here, of course we won't use FRP reinforcement in compression areas, but if you have steel reinforcement, let's say, so you can find out the strain at the level of the steel reinforcement, and you can also find out the stress that is related to the strain, that is the stress corresponding to the strain you find from the strain diagram. Make sense? Step by step. The next thing you will do is area times the stress. So in case of these layers, the area is area of this layer is this area here, times average stress is this stress here. So based on that you get a force. So you'll get 6 forces for these 6 layers, and in this case I am only showing one layer of reinforcement, and this reinforcement will have some strain at this level and the corresponding stress here, and the force is stress times the area in these 2 bars. Okay. Once you have done that, you have forces at different levels. Some of them above the neutral axis, all of them will be pointing left hand side. Below the neutral axis it will be pointing right hand side. That means this is compression, this is tension. So make sure you use compression is positive and tension negative, or the other way around, use compression negative, tension positive, and when you sum all of these you should get 0. So if it is not 0, that means you have to adjust your either your CB. If you adjust your CB, then you can get your equilibrium established. Okay. So for a given strain of epsilon c, once the force equilibrium is established, you can take moment about any point. It doesn't matter which point, any point in space. So you take moment about any point, any level here of all these individual incremental or small forces, and that will give you the moment capacity for that particular equilibrium condition. Does it make sense? It's very simple. If you do it once, you will not forget. So for over reinforced section, our strain here is 0.003. That's a given. So based on that, or 0.0035 if you are using IS 456, and then once you establish equilibrium, that C value is established, and then you get the moment based on the moment of small forces about any level. Questions? Questions? This is the easier one. Okay. The next one is the under reinforced section. In the under reinforced section, you'll actually have to do trial and error twice. Can anyone say why? Because the question is, for over reinforced sections, we just in one cycle of trial and error we were able to calculate the moment of resistance or moment capacity, right? But in case of under reinforced section, we had to do 2 sets of trial and error. Why? That's one thing, but that's right.
To limit the neutral axis depth.
Yeah.
So that we can ensure the under reinforced section.
Right. But remember, we talked about these strains in compression at the extreme compression fiber, right?
Yes.
In case of over reinforced section, that's defined. Right? We know that. That's 0.003 or 0.0035. However, for under reinforced condition, that strain is not known. Maybe less than 0.0035 or 0.003, depending on what code you are using. Therefore, you start with some strain, let's say 0.002, and then you repeat the process, establish the equilibrium condition, get your moment. Okay? And if it is under reinforced condition, what do you expect at the bottom? Strain at the bottom is FFU over EF, which is the epsilon FU. So it has to match, the strain at the bottom has to match with epsilon FU, or the stress at the bottom has to match with FFU, right? Until you match that, you have to keep going. So how many of you know the command in Excel spreadsheet? In Excel, there is a command called goal seek. How many have used this? So goal seek is a very handy, very useful command.